In the last few videos, we've talked about the elasticity of demand, a topic that isn't really related to this topic of related rates, but we're throwing them in the same section in our class. So we'll start out by thinking about these as completely different topics. Ignore all this stuff we just talked about, and we have a brand new topic here. But what you'll see is there are some connections between the two. Before I get into the connections, related rates. What's the idea with related rates? Well, as the name kind of implies, sometimes you have two different functions that are related to one another. So typically you think about a function as the result of a variable. My variable is time, and my function is the height of a rock that I throw up in the air as a function of time. It goes up, it comes back down. But sometimes, rather than think about a function as related to just a variable, it helps to think about a function as related to another function. The price that I'm going to charge will depend on inflation in the coming year. But inflation is not a variable, it's a function of time. It's something that changes over time. Sometimes, and I'll show you better examples as we go, we have two different functions that are related to one another. And when you're in that case, you might be interested in the derivatives of those related functions. When we talk about derivatives, we're talking about rates of change. But now it's not just for a single function, it's for two related functions. So we're taking derivatives of related functions to figure out the rates of change of those related functions, which gives us this topic, related rates. Okay, that was really confusing. Good news, we've already done this. In the previous two videos, I said you could think about revenue as price times quantity, right? Where price is the variable, it's something that you set, and quantity is a function. It's something that changes depending on your price. Revenue is a function, and it's equal to this variable, the letter P, times some other function, the quantity, my demand function. I got a function equal to a variable times another function. These two functions are related to each other. What if you wanted to know the derivative of this function, the derivative of your revenue function? Well, that's going to be super complicated because my revenue function is not just dependent on variables, it's dependent upon variables and functions. Well, good news, it's not that complicated. All you need to know is when we're taking derivatives of variables, the derivative is just equal to 1, right? We've seen this all over in this term. The derivative of x is equal to 1. However, when we're taking the derivative of a function instead of a variable, its derivative is not equal to 1. The derivative of q here is not 1, it's q prime. I don't even like writing this, but I'm going to write it because maybe it'll help. The derivative of q is equal to q prime in our language of this class. The derivative of my variable is just 1. The derivative of my function is q prime. Wait, how do I know if a letter represents a variable or a function? That's what this notation is telling you. This x right here is telling you that your variable is x. That's telling you that if you take the derivative of that letter, it should just be 1. Because this is not a q right here, the derivative of this q is not equal to 1. My variable is x, so q must be a function. The derivative of that function is q prime. If you're paying really close attention, you might notice that our symbol down here for derivative is slightly different than it used to be. We used to write d over dx, now I'm writing d over dp. Oh, that's strange, it's probably just a typo. No, this is specifying that p is the variable. What that's telling you is when you take the derivative of p, your answer should be 1, but when you take the derivative of q, your answer should not be 1, because p is your variable, q must be a function. This is the key to related rates. And all it says is treat letters differently. If that letter represents a variable, its derivative is 1. But if that variable represents a function, its derivative is not 1, it's q prime. And I know that seems confusing, but look, you let me get away with it before. Remember this line right here? We got this function is equal to this variable times this function. I'm using the product rule, which I guess I don't have to write again because it's written right here. I take the derivative of each of these things. The derivative of p, because it's a variable, is 1. Leave q alone. The derivative of q, because it's a function, is not 1. It's q prime. And then you leave p alone. If you're okay with this box, you are okay with related rates. To make sure you're okay with this, let me show you lots of related rates questions in a different context to make sure that you can follow. First one, the derivative of 5p. Be really careful here. This is telling you that p is a variable. What you've learned in this class is you treat this coefficient different. You pull that out in front, and then you have to take the derivative of that p. The derivative of your variable is just 1, so this is 5 times 1, or just 5. You're like, yeah, that's nothing new at all. That's exactly what I've been doing. Yes, but contrast that to this problem down here. Here we're taking the derivative. The way you say this is the derivative with respect to p, really just the derivative where p is the variable of 5q. How in the world do you do that? Well, we'll use the exact same rules that we learned. This 5 is a coefficient, so we can pull it out in front, and then all we have to do is figure out what's the derivative of the q. The derivative of the q, because it's not a variable, because there's not a q down here, is not 1. It's instead q prime. The derivative with respect to p of 5q is 5q prime. At the risk of confusing you, I want to make a couple comments about notation. Instead of writing q prime, some people write dq over dp. It means the exact same thing. I prefer this notation. It's just less symbols to write, but there are some advantages to this notation. This just means the derivative of this function q. But look what happens if you treat this d over dp thing as a fraction. D divided by dp, if it were a fraction and I was multiplying by q, I could think about that q as q over 1, and the way I multiply fractions is I multiply straight across. I would get d times q up on the top, and I would get d times p down on the bottom. If you really wanted to think about this operator as multiplication, this notation kind of lets you. And what's sort of cool is that if you did that exact same thing, but you were taking the derivative of your variable p, well, again, we could think about that p as p over 1 and multiply straight across, and we would have dp over dp, and when you have a fraction and the top and bottom of that fraction are the exact same, that's defined to be equal to 1, which is kind of nice because the derivative of a variable is just equal to 1. The reason these notations were chosen is so this would make more sense. Frankly, I'm of the opinion that it kind of just complicates the matter, and it gets students thinking about taking derivatives as some sort of weird multiplication, which really it's not. It just conveniently follows some of the rules of notation if you use the operators in this way. I think it's easier to just think about it this way. Q is a function, its derivative is q prime. If you can follow these first two examples, you can do everything you need with related rates, but it's kind of tricky, so we should work through a few together. What if you were taking the derivative, again with respect to p, meaning p is your variable, of 5pq? Can you figure out what that would be equal to? Well, my advice to you is go back to basics. Use the rules the way you're comfortable with. You know this 5 is a coefficient, so we can pull it out in front of the derivative sign. We got 5 times the derivative of p times q. Look at what you got here. It's a product of things. It's something times something. So use your product rule. We would get 5 times the sum of two things. One of those things would be the derivative of the first guy times the second guy, and the other thing would be the derivative of the second guy times the first guy. So I got 5 times the derivative of p, with respect to p, that's just equal to 1, times q, plus the derivative with respect to p of q, careful, that's not 1, that's q prime, or dq over dp if you want to write it that way, times p. We clean this up a little bit if we felt the need. Maybe don't write 1 times q, but instead just q. And if you want, you could get rid of the parentheses by distributing the 5 through. We'd get 5q plus 5pq prime. It's kind of fun once you get the hang of it. Let's do another one. The derivative with respect to p of q cubed. How could you figure that out? Well, what you want to do here is think chain rule. What you have here is something. It ends up being a function, but it doesn't really matter. You have something raised up to the third power. So your outer function is that raised up to the third power stuff. Using the chain rule, we first take care of that raised up to the third power stuff, completely leaving this stuff alone. Don't touch the q. The derivative of something to the third power is 3 times that something squared. But then you're not done. You still have to multiply that by the derivative of that something, q in this case. So I get 3q squared times whatever the derivative with respect to p of q is equal to. Well, the derivative with respect to p of q is just q prime, so I get 3q squared q prime. You starting to get the hang of it? If so, you might want to pause and try these 3 on your own. The derivative of e to the q power, Well, remember, chain rule told us that the derivative of e raised up to stuff is e to the stuff times the derivative of the stuff. So the derivative of e to the q would be e to the q times the derivative of that q. The derivative of that q is q prime, so I get e to the q power times q prime. What about the derivative of e to the p times q power? Well, again, we got chain rule going on here. We got e raised up to stuff. The derivative of e raised up to stuff is e raised up to stuff times the derivative of that stuff. But now be really careful. The derivative of that stuff is not obvious at all. We got something times something. We got to use the product rule. Fortunately, we've already figured out the derivative of p times q. We figured it out up here. It's just equal to q plus q prime p. So my final answer is e to the pq times q plus q prime p. How about one that's as hard as I can possibly make these? Probably more than you should ever have to do with related rates. How's that sound? Horrible, I'm sure, but stick with me. Can you take this derivative? I really encourage you to try it on your own. It's kind of fun, I promise. Actually, I don't promise. It's kind of a mess. But let's do it. Because it's such a mess, it might make sense to sort of take it one step at a time. So we have this 4 right here. It's a coefficient. Well, low-hanging fruit, I can take that 4 out in front, and then all that's left is the derivative of p times q times e to the p times q power. Wow, that's going to be a mess. It is, but maybe you could recognize that you're taking the derivative of a product of 3 different things. We had this superpower rule that said when you're taking the derivative of the product of 3 different things, just take the derivative of each one individually, leaving the other 2 alone, and then add up those things. What I'm saying is we'll have to take the derivative of the p, leaving the q and the e to the pq completely alone. And then we'll have to add to that the derivative of the q, leaving the p and the e to the pq completely alone. And then after we finish that, we'll want to take the derivative of the e to the pq power, leaving the p and the q completely alone. You know it's ugly when I can't even write it on one line. We got 3 derivatives left to take. Are they all derivatives we can take? I think so. This first one is pretty easy, right? The derivative with respect to p of p is just the number 1. So I get 1 times q times e to the pq. In other words, q e to the pq power. What about this second term? The derivative with respect to p of q is not 1, it's q prime. So I get q prime times p times e to the pq power. You're like, all right, this is going okay. What about this third one? Well, be careful here. To take the derivative of e to the pq power, you got to use the chain rule. In fact, it's exactly what we did in the previous problem. The derivative of e to the pq power is e to the pq power times q plus q prime p. So this first little part right here is all this stuff. E to the pq power times q plus q prime p. But then you're not done. You still have this p and this q to multiply that by. My final answer for this derivative is this huge mess right here. Could I simplify it? Yeah, probably, although I don't really want to. I think if it were me and I really cared about simplification, maybe I would recognize that all 3 of my terms have this e to the pq power in them, so I could factor that out in front and then just leave everything else as is, q plus q prime p plus. And then over here, instead of writing parentheses, I could take the pq and distribute it through. And I'd get pq squared plus q prime p squared q. Wow. Cool if you can see how this is equal to this, but really, if you can get this far, you know way more about related rates than you really ever need to know. If you can do the first few of these, you're doing fantastic with related rates. I think I want to call this video good. In the next video, I'll walk you through a related rates problem that's a little bit more applicable to our class, that will involve these ideas that we learned in all these examples, although I think you'll find that it's not quite as intense as these were.